Hello, what's up, everybody? It's me, Squirk, and we're going to talk about Taylor polynomials today. Okay, I had a little shift of gears in my brain recently, and I was like, let's go to Taylor polynomials. But before we do that, I thought maybe you'd want to see some datas from our Google form that I gave you last week. So here you go. How many of you guys missed math? It's good. 3, 4s, and 5s. That's what 33 out of 38 were kind of more than half missed math or at half. There's 38 responses. You see, it says that right here. Which personally I felt was kind of lame. That means that like 8 of you did not respond. So next time I want to see 46 right there. What's better, derivatives or integrals? People thought derivatives, 65 to 35%. During quarantine, mostly it was split between sleeping and social distancing media. Right there at 31.6. Kind of fun. The least amount wanted to have math homework. So sorry for that 10.5% that I let down. John Prine. John Prine is a real big deal to me. I've seen him in concert multiple times. I've listened to his music for decades, and when I heard that he had gotten coronavirus and was hospitalized, I knew that was going to be tough because he's had cancer twice and had part of his lung removed, and it was like, ooh, not a good case for him. So I've been playing a lot of John Prine, and all these words are in my head, and I thought, hey, let's pick one. The one that won there, you see, I'm too young to be where I'm going, but too old to go back again. That's from a song called Rocky Mountain Time. And there's a few lines in that song that are really cool. Another one that's in there that was kind of long, because it's like 2 stanzas, was the water tastes funny when you're far from your home, but it's only the thirsty that hunger to roam. That's in Rocky Mountain Time too. Great song. Tell me, where did the weekend go? I say that one a lot actually at school. Um, that's from the song called um, "Often is a word I seldom use. Went like thunder and it fell like snow." In third place there, "Humidity built the snowman, sunshine brought him down" is from the song "Humidity Built the Snowman." Um, and then "Please Don't Just Pass Him By and Stare" is from Hello in there. Great John Prine song. One of the first John Prine songs that I really knew all the words to and really made me fall in love with him. And "Far From Me," ain't it funny how an old broken bottle looks just like a diamond ring, but it's far, far from me, about a love that is disappearing when you don't realize it, you know? Anyway, I started a file called geometric. See, it's this one right here. That's where I put all those datas. But I decided to switch gears and to go into Taylor polynomials, this one right here. Because we've had 2 free response questions in the past, well, the last 2 that I've put up on the Googles, and they've dealt with Taylor polynomials. And I was gonna go, and my thought was to first finish out series, because that's what I usually do before spring break, is get through all the series stuff. And since we've been doing this online school, I jumped into Euler's method because we had questions on that. And I thought, well, that's a nice, neat little compact thing that we can do. But Taylor polynomials, as you see, it ties into series as well. But they don't have to. So we have Taylor and Maclaurin series. Scratch the series, make that polynomials. You can talk about Taylor polynomials and Maclaurin polynomials whenever you first learn derivatives. But when you get to the chapter on series, they'll talk about proving that Taylor and Maclaurin series converge for certain values, and we're not going to have to do that this year. And as I went running yesterday actually, and did not go by Vidu's house. Sorry, Vidu. Maybe today or tomorrow. But as I was running, it hit me. The series chapter is not including Taylor and Maclaurin series, but it mentions to know Taylor polynomials. And here we've had two examples of Taylor polynomial questions in the free response questions that I gave. So it's probably more likely that the Taylor question on this year's AP exam, and I'm guaranteeing you there's going to be a Taylor polynomial question on the AP exam. It's probably going to be in the part where there isn't series. And I don't know how this is going to be, honestly, but there's two questions. The first one is 25 minutes long, so I'm assuming that's going to have 4 or 5 parts to it. I'm thinking one of those parts is going to be Taylor polynomials, Maclaurin polynomials, which one of the two. And then you have another question that's 15 minutes long. And I'm thinking that one might focus on series, like just be series stuff. So we still need to talk about series stuff, obviously some more. But this Taylor polynomial thing, Maclaurin polynomial thing, we can do right here and now. And I think you might like. I actually think this stuff is really cool. I know I never learned this when I was in high school. I took quote BC calculus, but we did not do so much of the math that we have done in this class this year. And then I went to UK for 2 years and kind of wasted time. Did not take a single math class at UK. I did not know what I was doing with my life. I transferred to Bellarmine my 3rd year of college and then declared math major. But Bellarmine gave me credit for Calc 1 and Calc 2 because I did dual credit calculus through Bellarmine when I was in high school. I didn't take the AP exam. And back then, you could do dual credit for BC calculus. So I got Calc 1 and Calc 2 credit through Bellarmine, but when I went back to Bellarmine, the professors there probably would have said, hey, you didn't really learn all of Calc 2. So that's why they don't do that anymore. They don't offer BC for dual credit, only AB, and they don't do it at Bellarmine anymore. A lot of other colleges do. But anyway, Taylor polynomials are really cool. I think you might like this. Sorry, I've already wasted like a certain amount of your time. How long has it been so far? We haven't even started yet. Gosh, Martin, it's already been 6. Let's might as well start right here. We go. Ready? Here we go. 1, 2. Here we go. 7:13. Woo! 7:13. Okay. I'll make that go away. So 7:13. Now we can actually start the lesson. Maybe I'll put that in the notes. Jump to 7:13 if you want to start the lesson. Holy crap! Look at these notes up here. I can get as you're staring at this, you may be a little bit freaked out. I like to wait on Taylor and Maclaurin polynomials until we get to the series section. As I said before, you can actually do this stuff early. Notice really what you need to know to write a polynomial is that its coefficients, that would be the numbers in front of the letter, right? The number in front of the x. It's got a pattern of derivatives. So once you learn about derivatives, you can do Taylor polynomials. And these things are so cool. It's just easier to write this terribly long red string of terms in this big blue thing up here. See, the blue thing is a series. So it's a way to write the whole thing at once. So usually on the AP exam, when they give you a series question about Taylor and Maclaurin, they're going to give you, like they actually usually write this. It's usually on there, the formula. But as far as a Taylor polynomial goes, if you've seen 2 Taylor polynomial questions on the free responses I've given you, the one from 2012 and the one from 2009 were on this last week's free response questions. And they just asked, what is the second degree Taylor polynomial centered at 1 or centered at -1? I think were the numbers. We'll see them in a minute. So there's 2 big words that are important for Taylor and Maclaurin polynomials is the degree. So they tell you which degree to use, and also they tell you to center the polynomial about or center it at a certain value, okay? So that C value that you see in this formula, C, 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 right? The C value is the center. They're going to tell you that number. Okay, they're going to tell you C is 1 or 0 or -1. They'll also tell you to find the second degree Taylor polynomial. So second degree, just like it means from algebra 2, it means the highest power of the polynomial. Okay, so if they want a second degree, then you want it to be x to the second. So this blue series here, don't let that scare you. Okay, what you're going to learn to write is this formula, and you pretty much only need that much of it. And the good news about that formula that I just circled is it simplifies quite a bit down to right here. So what's in that box right there? Undo, 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 undo. What's in this box right here? That is your template for a second degree Taylor polynomial. That's basically what you're going to need to know, okay? The good news is this AP exam is open notes, right? You can use your notes because you're going to write up answers. Now, you don't want to spend 45 minutes looking through your notes because you only get 25 minutes to answer the question, okay? But there's the template. So how does this work? Notice that it says that the coefficients, the numbers in front of the variables, okay, deal with the derivative of the function divided by a factorial, and it's the nth derivative. So remember, when we put a number in parentheses and make it like an exponent, that actually means derivative, okay? That means derivative. So if it's the first derivative, we normally just write that as f prime. If it's a second derivative, we write it as f prime prime, right? If it's the third derivative, we can write prime prime prime, like I did down here, or you can put that little 3 in the parentheses, right? If it's the zeroth derivative, then you're talking about the function. The zeroth derivative is f, right? It's like, the function at time 0, which is the function f of x. So right now this is kind of weird because I'm giving you this big formula, and we're not doing a problem yet. So we're going to do a problem. The problem that's down below might make more sense of all this and what's actually happening. I am going to write a polynomial for some other function. As you see there, example 1, at the very bottom. The polynomial is going to be the sine function. So if you think about the sine function, it makes like the little squiggly, sign, like woo, 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 you know what I'm saying? Sine function, right? Dang it, it's already 11:59. Martin Joseph, this is going to be a long video. Sorry, guys. So this is the template that you're going to use. Okay, going back to the 0th derivative divided by 0 factorial. 0 factorial is 1, okay? So if I take the 0th derivative divided by 1, it's just f of c. Because notice this x minus c to the 0, that is also a 1. So in this first term, the denominator is a 1, and this thing is a 1, and all I'm left with is the 0th derivative, which is just f of c. So f of c is f of c, okay? But I wrote that term there. I wrote all this out in this way so you could see the pattern. Okay, the next term is the derivative at 1 divided by 1 factorial times x minus c to the 1, and 1 factorial is always 1. So you're just going to see that as f prime of c times x minus c, okay? And then the second derivative is f prime prime, right, divided by 2 factorial, and 2 factorial is just 2. You can leave it as 2 factorial, but I'm just simplifying it a little bit. And then x minus c squared. And then the third term, the next term in this pattern, right? I'm letting n go from 0 all the way up to infinity. So 0, 1, 2, 3. When n is 3, I get the third derivative at c divided by 3 factorial, which is 6, times x minus c to the third power, okay? So find the Maclaurin polynomial for f of x equals sine x. So there's two big dudes in the world of polynomial approximation of a function. And that would be Brooke Taylor, who is British, I'm like pretty sure, and Colin Maclaurin, who is obviously Scottish, and they would argue over ales and scotch, but those guys, Taylor was older. Brooke Taylor wrote like a book in like the early 1700s on like a polynomial approximation. He was kind of like the main guy. Colin Maclaurin was like 15 years younger than him or something like that. It's in our calculus book. Maybe I'll bring his picture up in a minute. And so not that these guys named these things after themselves, but I think that we call them Taylor and Maclaurin in honor of them. A Taylor series is centered at any number that you want it to be centered. You can center a Taylor series at 1, you can center a Taylor series at 0, you can center a Taylor series at 2, but a Maclaurin series is always centered at 0. So a Maclaurin series is a specific case of a Taylor series, okay? All Maclaurin series are Taylor series. but not all Taylor series are Maclaurin series, kind of like the square rectangle thing, right? So if you see the word Maclaurin, they're telling you that C is 0. The center of the polynomial is 0, okay? The center of the polynomial is basically like its point where we want to find the tangent line, if you will. So when you see Maclaurin, Maclaurin means that C is 0. I'm already on the pen, sorry. So Maclaurin, that word means C equals 0. And when C is equal to 0, these things are so much better, okay? So you see our formulas at the top. I'm going to fill that in. This is like a blank template. It's almost like a Mad Lib, but not as fun. And then what do I got to plug into that formula? Well, for every single C that you see, this C, 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 all those C's become zeros. Cool. But what is f prime of 0? I don't know. I need the derivative of f. What is f prime prime of 0? I don't know. I need the second derivative of f. So the first thing I'm going to do with any of this Taylor-Maclaurin stuff is I'm going to usually make a list of derivatives. Now, on the free response questions that we've seen that I've given you online, the last couple weeks, those problems were table problems. Like they gave you a table, I'm pretty sure. You didn't have to take a bunch of derivatives. But normally, like when you do problems out of Dr. Larson's book, you're going to need a bunch of derivatives. So if f of x is the sine of x, what is f prime of x? I need that derivative. What is the derivative sign? Cosine. What's the derivative of cosine? Because that's prime prime. The derivative of the derivative, prime prime. Derivative of cosine is negative sine. What's the derivative of the derivative of the derivative? Prime prime prime, right? Speaking of John Prine, the first CD he ever bought was called Prime Prine. Okay, so like prime is in like good stuff, like grade A, prime, prime rib, right? And his last name is Prine. So Prime is his greatest hits. That was the first CD I ever bought, and fell in love with John Prine with that. Derivative of negative sine is negative cosine. Now, what's the fourth derivative? Prime. Well, that would be negative sine, which is positive sine. So this right here is the fourth derivative of f. Then what's the fifth derivative got to be? It's this one, fifth derivative. And what's the sixth one? It's this one. What's the seventh one? It's this one. And what's the eighth one? I'd be back to the top, right? So that's how I write my derivatives, right? F with a little 6 in parentheses means sixth derivative. So let's just go about writing this string of derivatives out. I'm going to go back to red because I'm using my formula. Oh yeah, and so like the p sub n of x, I don't think I mentioned that when I was on the previous screen. The p sub n, the word p is used for polynomial. Sometimes they'll use a t for Taylor, okay? Again, this question, I could have said, find the Taylor polynomial for the sine of x about x equals 0. See, if you say the word Taylor, then you have to say what the center of the polynomial is, what the C value is. If you use the word Maclaurin, if you use the word Maclaurin, then that means the student is supposed to know, oh, C is equal 0. Okay, because you can't spell Maclaurin without 0. Actually, Taylor has an O in it, doesn't it? Anyway, Taylor means that C is 0. If it's a Maclaurin polynomial, C is 0. Okay, so sometimes you see T of X for Taylor polynomial, or you see P. Dr. Larson's book uses a P, but I think on the AP exam, like scoring sheets, they use the letter T, as the ones I've looked at over the years. But this just means a polynomial of like the first degree, P sub 1, when n is 1, that means I have first degree. Notice my question here on example 1, I didn't tell you the degree. I'm going to do a bunch of them so we can see a list, okay? Kind of see a pattern of how this works. So P sub 1 of x would mean f of c plus f prime of c times x minus c. And what is P sub 1 of x? Well, that means I need P sub 1 of x equal to f of 0 plus f prime of 0 times x minus 0. And what is f of 0? That means the sine of 0. That means the function at 0 times f prime of 0. What's f prime? That's cosine of 0 times x minus 0. And what is x minus 0? X minus 0 is just x. This is why I like Maclaurin polynomials the most. When the center is 0, you just get x every time. And again, it's x to the first power because I'm doing first degree, right? So the first degree is, this is going back to the very top of the screen. Notice this term right here that I'm boxing in. It's got the 1 there, okay? I don't have to write the 1, but maybe I should write it for this case. See, the 2 is on the next term. The 3 is on the next term because I'm doing first degree, second degree, third degree. Man, you're giving me the third degree, dude. So what is the sine of 0? You look up at the unit circle, which you can have printed out on a piece of paper sitting next to you for the AP exam because you get to use your notes on the AP exam. The sine of 0 is 0. Plus, what's the cosine of 0? That's 1. What's 1 times x? 1 times x is x, plus 0 is x. So the first degree Taylor polynomial centered at 0 for the sine function is the polynomial y equals x. Just x. What does that mean? What that means is, watch this, I'm gonna bump to the graph. Boom. The blue curve here is the sine wave, sine curve. Sine curve goes through 0, 0, right? It goes up to 1. Maybe hit trace. See, this is the sine curve. And I just found the first degree Taylor polynomial. So if I go down to y2, it's x. You might say, but that's just a tangent line, Mr. Quirk, and you would be exactly right. Turns out this whole freaking year, we've been finding equations of tangent lines. I could have called those, find the first degree Taylor polynomial to the function at the point, right? So the center, notice is 0, x is 0 is my center. At 0, the sine wave and the line intersect. They both contain the point 0, 0, right? See, 0, 0 blue, 0, 0 red, 0, 0 blue, 0, 0 red. If I do it fast enough, it looks purple. Anyway, first degree Taylor polynomial is a tangent line. First degree Taylor polynomial is a tangent line. If I go back to my notes over here, what I just did right here, if you think about it, this is y, and this f of 0 is the function's value at 0. It's kind of like my y1. If I move it back to the other side of the equal sign, it would then equal the f prime is the slope at 0 times x minus x1, which was the x coordinate, right? So the first degree Taylor polynomial is a tangent line. Find the equation of a tangent line. Equation of a tangent line is y equals mx plus b, or y minus y1 equals the slope times x minus x1. Okay, so what did Taylor and Maclaurin do that's kind of cool was they said, yo, bro, like, why are we going to stop at the line, bro? Let's find a tangent polynomial. Like, let's find a tangent parabola to the curve. Let's find a tangent cubic function. Of course, Taylor was was British, so he'd be like, hello, why don't we find a tangent polynomial to the curve, you know? Right? Cheerio. And then Maclaurin was like Scottish, so he was like, you don't know what you're talking about. It's not tangent line, it's tangent polynomial. Sorry. Good thing Radmaker's not here to laugh at me. So there's my first degree Taylor polynomial centered at 0, or I could call that the first degree Maclaurin polynomial. It's just y equals x. Now, if I want to go to P2, the second degree Taylor polynomial, I'm going to use this same strip of formula. I'm going to have the f of 0 plus the f prime of 0, x minus 0, and then I'm just going to tack on this next term, right? So I already know all this stuff right here, undo, undo, all this right here is just x. That's what it is. It's down, see, it's at the end of the line. So my P2 of x is, I just need one more term. I need to add the second derivative at 0 divided by 2 factorial times x minus 0, which is just x squared. And what is my second derivative at 0? Remember, the second derivative was negative sine x. So the second derivative at 0 would be negative sine 0. over 2. And what is the sine of 0? We talked about that already. Sine of 0 is 0. So it turns out for the sine function, the second degree Taylor polynomial is really boring. It's the same as the first one because this becomes 0. What's 0 divided by 2? 0. What's 0 times x squared? That means it doesn't have an x squared. So if you're asked to find a second degree Maclaurin polynomial for sine, it doesn't have it. But I bet it has a third degree. So P3 of x is going to be x, and I just need the third term at the end of the line here, the very top right corner. See that, guys? At this point, I'm hoping we're going to sort of recognize a pattern. Plus the third derivative, remember, was this one, negative cosine x. Plug in 0. What's the cosine of 0? 1. What's negative 1? Oh, Martin did it. What did I do? Oh, I hit a new page. Sorry, we're good. What's the cosine of 0? 1. What's negative 1? Negative 1 over 3 factorial times x cubed. That would be my third degree Taylor polynomial centered at 0 for the sine function. You may say, what do you mean by that, Mr. Quirk? Let's go to y equals. Notice number 4 here, enter graph. Is graphing a cubic function. A cubic function that has a negative coefficient, so it kind of goes down from left to right. The end behavior, right? It's like up on the left side, down on the right side. Algebra 2 stuff. So I just found, it's not perfect, but this third degree, I hit trace, we can see the equation at the top. Boom. This is negative 1/6 x cubed, right? Because 3 factorial is 6. 3 times 2 is 6. Negative 1/6 x cubed plus x is a cubic function. And that cubic function is tangent, if you will, to the sine function at the point 0, 0. Notice this pink function goes through 0, 0. Okay? If I were to now look at the differences, like let's go back to the original blue curve. And let's trace 0.5 on the blue curve. The sine function at 0.5 is 0.479, right? If I go to the red equation, that would be our first degree Taylor polynomial. That was just y equals x. If x is 0.5, what's y? On the red curve, if I plug in 0.5, y is also 0.5 because y is equal to x. We know that red answer right there, this y value, it's not exactly right. Remember, it was 0.473. Back to the blue. 0.5. I need to remember this number. 0.4794. 4794. If I go to the red curve, it's 0.5, right? 0.5 is a little bit off. Now let's go down one more to the pink curve and put in 0.5. Is it 0.4794? It's 0.4791, rounded, be 92, which is closer than 0.5, right? So by adding an extra term, my third degree Taylor polynomial, okay, it's approximating the function. So I'm approximating the sine curve with a cubic polynomial. And see, the thing that's nice about that is a polynomial is an easier function to evaluate, right? I can actually plug in 0.5 here. 0.5, right, minus 1/6 times 0.5 cubed. And what is a half times a half times a half? A half times a half times a half is an eighth. What's an eighth times a sixth? An eighth times a sixth is a 48th. And what is 1/2 minus a 48th? Well, I need to multiply by what? 24. So 24 minus 1 is 23 48ths. So what is the value of the sine function at 0.5? The sine of 0.5 is about 23 48ths. It's close to 0.5, right? 0.4791. But that's what this is all about. This polynomial approximation is like making a tangent line no longer a line. So what I'd like to be able to do maybe here is just follow this pattern. Remember P2 that didn't have a second degree, but so there won't be a P4 because if you go back, remember the fourth derivative in the top right corner, guys. See, I'm circling the fourth derivative was sine. And again, what's the sine of 0? Sine of 0 is 0. So the fourth term in this pattern is going to go away. But what's the fifth term going to be? See, so it's just x minus 1 over 3 factorial x to the third. The fifth term is going to be down here at cosine. And what's the cosine of 1? Notice this is positive cosine. Cosine of 1 is 1. So it's positive 1 over 5 factorial x to the fifth. So notice it goes positive x, then negative, and then positive. So once you start, and this is why this stuff fits into the series section so well. So remember, series is just summing up a sequence. A sequence is a pattern of numbers. So at this point, I hope you see the pattern. If you want the 11th degree Taylor polynomial centered at 0 for the sine function, it'd be x. Everybody say it together. Minus 1/3, or 1 over 3 factorial, x cubed, plus 1 over 5 factorial, x to the fifth. And what would come next after the plus? That's right, minus 1 over 7 factorial, x to the seventh, plus, because here it goes plus, minus, plus, 1 over 9 factorial, x to the ninth power, minus 1 over 11, x to the 11th. I forgot the factorial. Factorial x to the 11th. This thing down here is a polynomial. Polynomial. But it's approximating the sine curve. Okay? And to save time, actually, I didn't graph all of these, but I have the graph here. So, hold on a second. Well, I'll go back to it. Here's the graph. Look at this. So we already saw earlier the blue, the red, and the pink one. And I think I need to zoom. I zoomed in too much. There we go. The blue f of x is my original function. The sine function is pretty much disappeared. It's been covered up by these other colors, right? The red curve was the tangent line, tangent at 0, 0, or we use the word centered. So P1 of x is the polynomial centered at 0. P3 of x is this pink one, which is a cubic polynomial, third degree polynomial centered at 0. P5 is up here, the green one. Okay, so after the pink one, the green one, you notice, is closer to the sine curve. Okay, for longer, see the pink one's spaced out right in here, but the green one is closer. And then after the green one, we go over here to P7 is this orange curve, which is even closer than the green curve. See, the green curve is away from the sine function, but the orange one's closer. And then the ninth degree Taylor polynomial centered at 0 for the sine function, right, is this one. It's kind of orange, it's brown. P sub 9, the ninth degree Taylor polynomial. So you can see, and then if I were to put the 11th one on here, I didn't do that, and the 13th and the 15th and the 17th, it's kind of interesting to think how we're turning this transcendental function, sine, right? Oop, Martin, what are you doing? We're turning this sine function, right, into a polynomial function, which is pretty awesome because it's conceivably or theoretically easier to approximate a sine function using polynomials, to use terms instead of, because like, what's the sine of 2? I don't know. Now that brings up something else here that, the further you get away from your center, where's my graphing calculator? The further you get away from your center, right? So back to the blue one, if I go to say 0.9, 0.9 is pretty far away from 0, right? Notice the blue curve's value, the sine's value, the actual function's value at 0.9 is 7, right? 0.7. Let's go to 1 radian. The sine of 1 is 0.84, right? But on the red curve, when x is 1, y is 1. And that 1 is pretty far away from 0.84, way further away than 0.5 was from 0.47, right? Notice if I go to just the third degree, add one term to that red function and go to 1, plug in 1, right? 1's pretty easy here because it's just 1 minus a sixth, and 1 minus a sixth is 5/6, right? So 5/6 is 0.833333, which, remember, the actual sine of 1 was 0.841. See, I'm approximating the sine function. So like, if I were to ask you, what's the sine of 1? Without a calculator, you really couldn't do it. But if I just give you this simple function, that's here, I keep forgetting where I'm going. This one right here, right? It's very easy to approximate. In fact, pick a different color. I'm sure you guys are tired of looking at the red. What is P3 of 1? That would mean you plug in 1 for x minus 1/6, because 3 factorial is 6 times 1 cubed. And what is 1 cubed? 1 times 1 times 1. So it's 1 minus a sixth. And 1 minus a sixth is 5/6. And I could even figure out 5/6 like in my head by doing long division is 0.8333333, you know, but I can't figure out the sine of 1. So this stuff is super duper cool to me. Sorry, this is going to take a long time. How long have we been? Oh man, 35 minutes. I got a bunch more examples to go. Hi guys. Okay. So I'll rip through them fast. But if I go really far away, like let's go back to here, and what in the heck, you know, to the blue curve, the sine of 3, right? The actual sine of 3 is 0.1. If I go to the red curve, obviously when x is 3, y is 3. So 3 is very far away from 0.1. And then if we go to the third degree Taylor polynomial at 3, it's a negative, right? Negative 1.5, which is kind of weird number because we want the answer to be 0.1, right? So the sine of 3 is 0.1. So the further you get away from your center, your approximations are obviously worthless, right? You have to be close to your center. So I made up an example to do next. So we're back to this graph. So this right here, I think this graph is super cool. I love that. It reminds me of like some sort of like crazy trig octopus thing. I'm coming at you, you know? Coming to get you. I'm coming to get you. Spitting out lyrics on me, I'm with you. You know what I'm saying? Okay, so this is what we're gonna do. We're gonna go fast. Find the third degree Taylor polynomial for ln of x about x equals 2. So I'm giving you an example to do on your own, okay? I think I have this one worked out already. Find the third degree. So third degree means you want, oh, that's something I meant to mention before up here, right? Third degree. What does third degree mean? You guys know this. It means you want the power to be 3, right? Notice here, right here, x is to the third power, okay? Third degree. Sometimes they get tricky with the question, and they won't say find the third degree Taylor polynomial, but they'll say find the first 3 terms of the Taylor polynomial. Okay, so for the sine function, if you're asked to find the first 3 terms, the first 3 terms would mean which degree? The degree with 3 terms is this one, right? 5th degree Maclaurin polynomial for sine has 3 terms. Now, on our 2 examples that we've seen so far of free response questions that I've posted online, they both use the word degree. Degree is definitely better than number of terms, but you do have to be careful with number of terms. Sometimes they'll say find the first 4 terms of the Taylor polynomial, which could mean 4th degree. It could mean 3rd degree, right? Or in this case, it would mean 7th degree if it's a sine function. It all depends on the function you're using, okay? So number of terms versus degree, that's what that's about. So I made up a problem down here. Find the third degree Taylor polynomial for Ln of x about x equals 2, period. Okay, about x equals 2 means that 2 is your center. Centered at 2 is another way they could say it. That means c equals 2. So x equals 2, c equals 2. Yeah, my point of tangency is at 2, right, when x is 2. So what do you got to do here? I would suggest first thing you do is write down the formula. Remember our formula for a Taylor polynomial. And if you write this one down, then what you see right there in blue, a piece of paper, and keep it close by, that should be all that you really need for the AP exam. I can't imagine them asking you to find a 4th degree or a 5th degree or 6th degree. It takes such a long time. Normally it's going to be a 2nd degree or 3rd degree. This is the formula for a 3rd degree Taylor polynomial. Notice it's centered at 2, so you can't use the word Maclaurin here, right? Maclaurin doesn't get to play. Maclaurin's like, hey, put me in. I want to get the game. And Taylor's like, back off, bro. It's x equals 2, you know? So this is our template. You're going to fill in this template. At this point, I want you to pause it. Pause this video. Okay, pause. Pause it. Because I want you, well, don't pause it yet. I want you to find this answer. Find the 3rd degree Taylor polynomial for Ln of x. That's your function. F of x is Ln of x. That means you're going to take a bunch of derivatives. Okay? You take a bunch of derivatives. You're going to need derivatives, up to probably 3rd derivative, by the way. So what is the derivative of Ln of x? What's the 2nd derivative? What's the 3rd derivative? You're going to make derivatives. Okay? And I got those down. I got them down here. So I want you to pause it. See, there's my f of x equals ln of x. If you forgot what the derivative of ln of x is, shame on you. Go back and look it up. And then make a list of all your derivatives and all your integrals and keep it right there by your notes, because you get to use your notes on the AP exam this year, right? Make a list of derivatives, fill in the template, pause the video now. You better paused it. Okay, so you unpaused it. Okay, now hit unpause. If you haven't already unpaused it, unpause it now. Dang it, how are they going to know to unpause it? Because if it's paused, they're not going to hear me say unpause. Oh well. Third degree Taylor polynomial for the function ln of x. So notice my function is a natural log. That's a weird function. That's actually what's called a transcendental function. A polynomial is an algebraic function. A polynomial is x's to powers. So this is my third degree. Notice it's centered at 2. That means you're going to have a bunch of x minus 2s, 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 x minus 2s. Okay. So that's the answer. Notice the f of c, right, is ln of 2, because it's f of 2. F of 2 is the ln of 2. So if I were to look at this graph, and I have it here, boom, boom, turn this one off and turn this one off, and turn this one on, and turn this one off. I did try to save time and type all these in earlier. These are the ones that I typed in earlier to graph, but way down here, look, I had f of 9 hiding. There's the ln of x function. I'll pause it. That is the ln of x function. The regular natural log, it has an asymptote at the y-axis. It goes through the point 1, 0. That's its x-intercept. Okay. And then what is the Taylor polynomial? Third degree Taylor polynomial, right? So ln of x is the black one. If I go up, here's our ln of 2 plus 1/2 x minus 2 minus 1/8 x minus 2 squared plus 1/24 x minus 2 cubed. So this is a cubic function, cubic polynomial. Notice at 2, if I trace 2 on the black curve, I get 0.6931, 0.69 pi 72. If I go up and trace 2 on the red curve, it's the exact same thing. It's the ln of 2, right? Because going back to our equation here, right? If I plug 2 in here, it cancels out. If I plug 2 in here, 2 minus 0, 2 minus 0, those all cancel out. This is the part of the series stuff that we get to skip. Is it turns out these Taylor and Maclaurin polynomials converge obviously at their center. See, if I plug in 2 for everything, right, then this series, no matter, even though that it goes on to forever, right, because there's a plus infinity here technically, right, it's always going to converge when x is 2. When else would this series converge? Well, it could converge for other values of x, like maybe when x is 1.2 or when x is 2.1, right? So that's stuff we don't have to do anymore. That's all power series stuff and interval of convergence and radius of convergence. And I'm sad we don't get to do that because it's fun. But I'm just using the example. So if I plug in 2, all this stuff cancels out and all I have left is ln of 2. So obviously the function ln of x when x is equal to 2 equals ln of 2, right? Back to the black one. When I plug in 2 for x, y equals the ln of 2. That is the ln of 2 right there. If I go up to the polynomial function, this is a cubic function, and plug in 2, I get the same 0.69 pi 72. Okay, but what I can now do with the polynomial function that's really hard to do with the ln function is plug in other numbers. Like, what is the ln of 2.5? I have no idea. I can't do it without a calculator. Euler could do it because he was like freaking genius. But think about it, those guys had nothing else to do back then. Like, you probably heard this between now and when we got out of school, that like when Newton got quarantined or something happened, I don't know, Newton got like, the flu. That's when he invented calculus because he was like stuck at home. I don't know, it's probably all lies, but still. The ln of 2.5, we don't know how to do that in our head. The ln of 2.5 is 0.916. If I go to the polynomial and type in 2.5, it's 0.917. See, they're very, very close. The polynomial is approximating the function. Now, the further I get away, like let's go back to 4. What's the ln of 4? 1.38, right? What's the polynomial of 4? 1.52, right? What's the ln of 5? The ln of 5 is 1.609. On the polynomial, when I go to 5, you see the red curve goes off the top of the grid. So it's not 1 point something, it's 2 point something. So the further I get away from my center, the further you get away from 2, at 2, they're exactly the same. Just like a tangent line and a curve. They're the same at the point of tangency. The further you get away from the point of tangency, the line becomes less accurate. If you use a polynomial instead of a line, then boom, you're there. So we pretty much got it. Pretty much done. So jumping back to here, what do we have left? So the rest of these I already worked the answers out. No, I didn't. Dang on it. I was hoping we could end this video now. So if you want, pause the video, go get something to eat, come back, watch it, the rest of it tomorrow. Here's the FRQ from 2012, where you had to find in part D. This is the one part we hadn't finished yet. This is partly why I decided yesterday, hey, why don't I just do the Taylor polynomial stuff? We'll worry about series, later. So Taylor polynomial for f of x about x equals 1, okay? Use the Taylor polynomial to approximate f of 1.4. It's like we were just doing with that natural log function. 1 and 1.4 are really close to each other, right? So I can approximate the function at 1.4 by using this polynomial. I can approximate, and what's happening here on the AP exam is kind of neat. It's not a weird transcendental function like sine or log, but we don't have the function. We don't even have f of x. We have a table of rates. We have a table of derivatives. And so finally, this thing right here, people might be most infectious with coronavirus before they show symptoms. Yeah, we knew that already, didn't we? This thing right here is going to become important all of a sudden. The second derivative, we hadn't touched that thing yet, right? They told us in the very beginning of this problem, f prime prime of 1, and you didn't need that at all for part A, B, or C. So how do we write the second degree Taylor polynomial? Again, if you need to, pause it and work this out. I actually had worked this answer out already, and then I erased it. I thought we'll work it out together, but this kind of stinks because now it's going to take this video and make it longer. Remember, the second degree Taylor polynomial is f of c plus f prime of c over 1 factorial times x minus, c to the first plus f prime prime of c over 2 factorial times x minus c squared. So that is a polynomial. This time it is a Taylor polynomial centered about x equals 1. So what does that about x equals 1 mean? Oh, come on, auto saving, please. That means c is 1. C is 1. It's centered about x equals 1. The center is 1. C is 1. So just fill in all the parts now. Second degree Taylor polynomial of x is first f of 1 plus f prime of 1 over 1 is just 1, so I don't need that, right? I'll put it there. X minus 1 to the first plus f prime prime of 1. F prime prime of 1 divided by 2 factorial is just 2 times x minus 1 squared. I'm almost done. That pretty much counts for the first half of this question. Second degree Taylor polynomial is f of 1, and what's f of 1? We were told that way up here. F of 1 is 15. Plus, what's f prime of 1? F prime of 1. F prime of 1 comes from the table, right? It's 8 times x minus 1. Plus, what's the second derivative at 1? I don't know. Oh, yeah, I do. That's right. They gave you this 20. Finally, we could use the 20 over 2, because 2 factorial is 2, times minus 1 quantity squared. So hopefully maybe you already worked this out. You paused the video, you worked it out. Can we simplify that a little bit? It is 15 plus 8 times x minus 1 plus 10 times x minus 1 squared. Oh, that was ugly. 1 squared. That is the second degree Taylor polynomial. That right there, and the way this was scored, that was 1 point. Just being able to write that's 1 point. And the more you practice this is super easy. I really like this Taylor Polynomial stuff. I think it's tons of fun. Now we're supposed to use that Taylor Polynomial to approximate the function. Do I have room down here? I don't have a lot of room down here. I'm going to go up. So let's go up with purple. I'm going to plug in 1.4. 15 times 8. What is 1.4 minus 1? That would be 0.4. Plus 10 times. What's 1.4 minus 1? That would be 0.4 squared. What's 0.4 times 0.4? Well, 4 times 4 is 16. So 0.4 times 0.4 is 0.16 because you move the decimal twice. And what's 0.16 times 10? That would be 1.6. And what's 8 times 0.4? Well, that's 3.2. And what's 15? 15. I'm going up. So what's my final answer? 15 plus 3 is 18, plus 1 is 19, and 0.2 plus 0.6 is 0.8. So the Taylor polynomial approximation of the function at 1.4 is 19.8. Whew. That finally answers this question from 2012. So we got part C was Euler's method, part D was Taylor polynomials. We could do parts A and B. You might think, what was part A and B? I don't remember. Guess what? I have it right here. So just to talk about part A real quick. Remember part A said to write the equation of a tangent line. Notice our tangent line that's right here, right? It's 8 times x minus 1 plus 15. Exactly what I have right here, right? 8 times x minus 1 plus 15. So the first degree Taylor polynomial is the same thing as the tangent line. Okay? Second degree Taylor polynomial turns it into a quadratic. So part A, we were approximating the function's value at 1.4. And I would just use these first three terms, which looking back here, right, is 15 plus 3.2. It was 15 plus 3.2. 15 plus 3.2 is 18.2, right? So that was our answer for part A, 18.2. In part D, we have a better approximation, 19.8. How do I know 19.8 is better? Well, because it's more terms. But when you look at part B and part C, which I have them on here too, same thing. Part B, we're supposed to use the midpoint Riemann sum. Okay, how's that work? Remember, a Riemann sum is like integral. So when you integrate f prime, you get f, right? When you integrate f prime, you get f. So when I find the area under the curve using the Riemann sum, right, rectangles, right, the area under the curve is 14.6. What do I have to do to the 14.6? I have to add the original value back onto it, where it is at 1, right? At 1, it's already at 15. My 4.6 is going to take me up 4.6 more. So it's 19.6, which is a whole lot closer to this 19.8, you know? Now, which one's exactly correct? Neither of them are exactly correct. They're both approximations. And then Euler's method was part C. Same problem, 2012, part C. Euler's method, the answer was 19. Remember, Euler's method is where you took the steps and you went over a delta x and you went up a delta y. And so I took 15 plus my delta x of 1.6, which I got from the slope, right? And got 16.2 or 16.6, sorry. And then from there, this is a mistake that some people made on their Euler's method math, was now you want to start back over at 16.6. See how that number here is from here? You put that down here as a new y. So 16.6 plus my new delta y, 2.4, is 19. So I very much think this 2012 free response question is going to be a lot of what you may see on the AP exam. You have rectangles, Euler's method, tangent line, and Taylor polynomial. That's so much of calculus, like especially BC calculus. Euler's method and Taylor polynomials are BC topics. The Riemann sum with the rectangles, that's AB, and tangent line is obviously AB. So look, here's our next question. Consider differential equation. This was on the problems I gave you guys on Friday, okay? FRQs to cure the COVID blues, right? This was example 2. This was actually from 2009 BC test. This was question 4. So at this point, I have the answer worked out here, so I don't have to you don't have to listen to me work it out like you did the last one. Sorry. You pause it and work this out. Notice here they don't ask you to approximate the function using another value. They just want the second degree Taylor polynomial. So second degree Taylor polynomial is just like what we did up here in the last free response. Notice I happen to tell you the value of d2y dx2 is negative 12. You may think, well, that's interesting. Why'd they tell me that? It's because you're going to need second degree, which requires f prime prime, right? Of course, they didn't write it as f prime prime because d2y over dx2 looks more confusing, right? So remember, that just means f prime prime of x. And you have dy dx right here. This notation, the d2y over dx2, is also used more often when your function is implicit like this, okay? So I wouldn't really say f prime prime of x in this situation because this is not a function of x, right? See, it's got x's and y's. So that means that y equals was probably not a function of x either. It was a function of x and y, which I think they ask you to do in part C of this problem, which I'm going to post the answers to these other for response soon. They want you to actually find what y equals, right? Or as exponential, I think. Anyway, so shut up, Marty. Pause this, see if you can find the second degree polynomial, and I'm gonna like then put the answers up here, and now you hit unpause and you're checking your answer. So the tricky thing here was you have to find f prime of -1, which equals 4. That's what goes in here. F prime of -1 is 4. The second derivative was -12. The second degree Taylor polynomial is 2 plus 4 times x plus 1 minus 6 times x plus 1 squared. That was my last example. Whoops. That was our lunch group today. Here, you can pause it here if you want to look at this. And then when you hit pause, you'll see our lunch group. We had lunch today. This was our C lunch bunch minus Mr. Canali. So I screenshotted our lunch. We always eat in Mr. Thomas's room. So all my 6th period BC calc, woo, let me hear you. You know, they're always waiting. 7th period wouldn't know this. They're always waiting at the door for me because I'm always walking back from Mr. Thomas's room, and I'm usually like the last one because it's, you know, I walk slow. There's usually 8 of us, and Mr. Canali for some reason was too cool to like join us for lunch today. So there's all my homies. This has been a very strange time. I love you guys, and I miss all you guys, and I know you miss each other way more than you miss me probably. That was the last example that I had here for that Taylor polynomial. Okay, I'm gonna stop this video in a second. I'm gonna give you some problems out of the Larson book. Okay, notice the Larson book. This is 9-7 is in the series chapter, but this is the Taylor polynomial stuff. Notice question 1 through 4 wants you to match the graphs. I might give you that just see if you can figure that out. Notice the function is this black like kind of like little humpy like mountain molehill here, right? And then you're matching A, B, C, and D. He's got some problems in here that are kind of like notice he asked you in 5 through 8, find a first degree Taylor polynomial. And then they ask you to figure out what is this first degree Taylor polynomial called? Well, we've actually already talked about that. If it's first degree, it's the same thing as finding the equation of the, very good, I heard you say it, tangent line. So that's tangent line. Just find the equation of tangent line on 5 through 8. So that's kind of boring. We've done that a lot. Over here is where it gets into the fun stuff. So notice on 13 through 24, find the nth Maclaurin polynomial. So on 13, nth means degree. So that's the 4th degree. On 13, the 4th degree Maclaurin polynomial. Since it's Maclaurin, that means C equals what number? Very good. 0. I heard you. But then you jump down here to 25 through 30. Find the nth degree Taylor polynomial centered at C. So you notice on 25, they give you an n number and a C number. Whereas up here in 23, there's just an n number because C is 0. I like it when C is 0. It's much less writing and things are kind of gooder when you use 0. But I'll probably give you some of these problems for homework, okay? I'm going to stop now. Oh, look, it's just under an hour. This was easy. It's just like regular class. If I was to try to go the whole time, I would have run out of time. You know? So anyway, have a nice time. I miss you guys. I hope you're doing good. Holla.